Hi, let's start with matrices. According to all the bookish definitions, a matrix is a system of mn numbers arranged in the form of arrays with m rows and n columns. Generally, matrices are represented by capital letters and it is written in the form of A equals Aij, where I represents number of rows and j represents number of columns. Matrix can be of any size, 2 cross 2, 3 cross 2, 1 cross 2 or any size. There are some special type of matrices. Let's talk about them. The first is the square matrix. In a square matrix, number of rows equals number of columns. So when we write A equals Aij having a dimension of m cross n, so in a square matrix m is equals to n. Let's see some examples. Suppose A equals 1, 2, minus 1 and 0. See, in this matrix A has a dimension of 2 cross 2. So number of rows equals number of columns. Let's see one more. B is equals to 1, 2, 3, 1, 0, 0, minus 1, 2, 3. So B is a 3 cross 3 matrix with 3 rows and 3 columns. However, consider the places where row number is equals to the column number. So suppose this place, row is 1 and column is 1. This place where row is 2 and column is also 2. Here where row is 3 and column is also 3. All these places are called diagonal elements and the line along which they lie is called the principal diagonals. So let's say in this matrix A, we have the 1 and 0 as the diagonal elements and the line along which they lie is called the principal diagonal. Let me construct one more matrix C. Suppose 1, 2, 1 and 0. I have constructed C out of B. So 1, 2, 1 and 0. Make a note that the diagonal elements of C is also the part of diagonal elements of B. So whenever this is the case, C is called the principal submatrix. So this is very important property. It will be helpful while solving questions. Whenever the diagonal elements of submatrix is a part of diagonal elements of the original matrix, then the submatrix is called the principal submatrix. Okay, let's talk about diagonal matrix. In a diagonal matrix, all the non-diagonal elements are 0. Just make a note that all the non-diagonal elements of 0. However, the diagonal elements may or may not be 0, but all the non-diagonal elements have to be 0. So we have A equals 1, 0, 0, 0, 3, 0 and 0, 0, 5. So only the principal diagonal elements are non-zero. Rest all the elements are 0. So A has the order of 3 cross 3. So there is a handy way to write this. Just write diag and write the elements along the principal diagonal. That's it. You don't need to write the full matrix because all the elements are 0. Only the elements along the principal diagonal are non-zero. So write diag 1, 3 and 5. That's it. Let's see some of the properties of diagonal matrix. Suppose you have to add the two diagonal matrix, so diag 1, 3, 5 and you have to add it with diag 3, 5, 9. So whenever this is the case, just write diag and add the corresponding elements. So we have 1 plus 3, that is 4, 3 plus 5, that is 8, 5 plus 9, that is 14. So this is the addition of two diagonal matrix. Similarly, suppose you have to multiply two diagonal matrices. I know we haven't covered multiplication of matrices yet, but this is very simple. So just write diag and multiply the corresponding elements. So 1 into 4 is 4, 3 into 5 is 15 and 5 into 9 is 45. That's it. Next, suppose you have to find the inverse of diagonal matrix. So just write diag and take the reciprocal of corresponding elements. So this is 1 over A, 1 over B and 1 over C. Just make a note that these properties are only applicable for diagonal matrices. It is not applicable for all other matrices. Next we have diagonal matrix and you have to raise it to the power of n. So write diag and raise each element to the power of n. So A to the power n, B to the power n and C to the power n. That's it. And finally, suppose you have to find the determinant of a diagonal matrix. So just multiply the corresponding elements of principal diagonal. So x, y, z will be the determinant of diagonal matrix. Let's talk about scalar matrix. Scalar matrix is a special case of diagonal matrix where all the elements are equal. So let me write an example to make it more clear. So we have A equals 1 0 0 0 1 0 0 0 1. So see, A is a diagonal matrix and all the elements are equal. So A is a scalar matrix. Okay, that's it. This is very easy and there is no much more to talk about it. Next we have the unity or identity matrix. In identity matrix, all the diagonal elements are equals 1. Just make a note that there is a small difference between unity matrix and scalar matrix. In scalar matrix, all the elements are equal. However, it is not compulsory that they have to be 1, 2 or 3. It can be anything. But in unit matrix, all the elements have to be 1. So we have A equals Aij. So to generalize it, I'll write A equals Aij, which is equals to 1 when I equals j, and it is equals to 0 when I is not equals to j. That's it. Let's see some example. Before that, let me tell you, unit matrix is denoted by I. So we have I3 equals 1 0 0 0 1 0 0 0 1. I2 equals 1 0 0 1. So this is some of the example of identity matrix. There are some handy properties of identity matrix. Let's talk about them. I is the multiplicative identity for a matrix, which means that if you multiply I with A or A with I, you will get A itself. If you raise I to the power of n, you will get I itself. If you have to find the inverse of I, then it will be I itself. And finally, if you have to find the determinant of I, then it will be 1. That's it. Let's talk about null matrix. Yeah. So a matrix of order m cross n where all the elements are 0, then it is called null matrix. It may or may not be a square matrix. Let's see an example. It is represented by O. So O equals 0 0 0 0 0 0. So this is a null matrix of order 2 cross 3. It may or may not be a square matrix and all the elements have to be 0. That's it. Let's see some properties of null matrix. O is the additive identity for any matrix, which means that if you add O with A or A with O, you will get A itself. Also, if you add A with the negative of A, you will get a null matrix. So minus of A is called the additive inverse of A. Let's talk about upper triangular matrix. In upper triangular matrix, all the elements below the principal diagonal are 0. So let's see, A equals 1 2 3 0 minus 1 2 0 0 4. See, all the elements below the principal diagonals are 0. So to generalize it, I'll write A equals Aij when I is greater than j, then Aij will be 0. Let's see. We have I equals 2 here and j equals 1. We have I equals 3 here and j equals 1. So this is 0. And here we have j equals 2 and I is 3. So whenever I is greater than j, Aij is 0. So this is called the upper triangular matrix. Let's talk about lower triangular matrix. In a lower triangular matrix, all the elements above the principal diagonal are 0. So let's see. A equals 1 2 0. Oops. So we have 1 0 0 2 3 0 minus 1 4. So see, here all the elements above the principal diagonals are 0. So to generalize it as above, we'll write A equals Aij, and when I is less than j, then Aij will be 0. So let's see. Here I is 1, j is 2, and here j is 3. So this is 0. Here I is 2 and j is 3. So here this is also 0. So whenever I is less than j, Aij will be 0. That's it in lower triangular matrix. Now let's talk about idempotent matrix. So this is an important one. Whenever a square is equals to a, so just remember this property, whenever a square is equals to a, the matrix A will be called an idempotent matrix. Let's see one example to make it more clear. So suppose we have a equals 1, 0, 0 and 1. So this is an identity matrix of order 2. A while ago we saw that whenever we raise identity matrix to the power of n, we will get identity matrix itself. So we can raise a to the power of 2 and we will get a itself. So here the matrix A is an idempotent matrix. Okay, I'll give you one example. You can try it out yourself. If you face any difficulty, you can reach out to me. I'll help you out. So this is a matrix of order 3. Just find it out a square and check whether this is equals to a. If this is true, then a will be an idempotent matrix. Next we have involuntary matrix. Whenever a square is equals to I, we will say a is an involuntary matrix. Again, we'll see one more example. Suppose a is 1, 0, 0, 1, 0, 0, 0, 1. So whenever this is the case, this is equals to identity matrix of order 3. So we know that if we raise I to the power of 2, we will get I itself. So here we can say that A is an involuntary matrix. So whenever this is the case, when A square is equals to I, we say that A is an involuntary matrix. Okay, I'll give you one example. You can try it out yourself. A equals 4, 3, 3, minus 1, 0, minus 1, minus 4, minus 4, minus 3. Find the value of a square and check whether it is equals to I. If you face any difficulty, let me know in comments. I'll help you out. And finally, we have nilpotent matrix. So this is an important one. So we have a matrix A, and if a to the power of x is 0 and a to the power of x minus 1 is not equals to 0, then we say that A is a nilpotent matrix of order x. X is the smallest element for which A is a nilpotent matrix. Just make sure that x is the smallest element for which A is nilpotent matrix. Let's see some example. Let's see one example to consider it. So suppose A is 1, 1, 3, 5, 2, 6, minus 2, minus 1, minus 3. Okay, so this is a matrix A of order 3 cross 3. Okay, just pause the video and try it out yourself. I have already calculated, so I know the result, but you pause the video and try it out yourself. So when you calculate A square, it won't be equal to a null matrix, and clearly A is also not equals to a null matrix. Then we find out A cube, and when you calculate A cube by A square multiplied by A, then you will get A cube equals to a null matrix. So here we can say that A is not equals to a null matrix, A square is not equals to a null matrix, but A cube is a null matrix. Then A is a nilpotent matrix of order 3. So 3 is the smallest integer for which A is a nilpotent matrix. That's it for this lecture. In the next lecture, we will talk about equality of matrices and addition and subtraction of matrices.